Hi everyone, welcome to RFI Data Science. So last time we have seen about lasso regression, and we have already used lasso for predicting our biomedical literature data, which was retrieved from PubMed. And this data is about COVID. It's mainly an abstract of scientific publications, and half of them are about COVID and half of them are about SARS. So we have used lasso regression, and we have seen actually it worked well for prediction. And actually, until now, we have seen several different models. We have seen naive Bayes and support vector machines with different kernel strategies. And last time we have started using regularization methods, regularization techniques. So we have seen ridge regression, and also we have seen lasso. Today we will continue and we'll use elastic net regularization. And as we remember from our theoretical intuition tutorial of our ridge and lasso regression, and we have said lasso is an effective way of handling feature selection. So it effectively selects features because it pushes irrelevant features towards actually to all the way to zero. So all the irrelevant features will be pushed towards zero, and their coefficient will be zeroed out, and they will not be in our final model. That's one of the typical advantage of lasso, because it facilitates, it automates feature selection process. The problem with lasso is when you have correlated features, what it does is one is pushed towards zero and the other one is retained. And this process of retaining one variable and the other one pushing the other one towards zero is not really systematic, and that's why lasso has this limitation. And at the same time, ridge actually is actually effective in handling these correlated features. So that means ridge is effective in handling correlated feature, while lasso is effective in handling feature selection process. Now, the two of them, they have some kind of limitations, but there is a good model, that's elastic net, which combines the two advantages. So you combine the two advantages of lasso, the advantage of lasso, which is effective feature selection, and the advantage of ridge regression, which is about effective regularization method. So that is what elastic net comes to play. So the elastic net regularization is what you do is, if you know the ordinary least square regression, the objective function is sum of square errors, and then on top of that you do the L2 norm, and then another one L1 norm. That means one is for ridge regression, which penalty term, and you add another penalty term for lasso. So this will be an effective method for regularization and feature selection. So for today, we will use the same data, the same text analysis pipelines that we have already done in the past, and we will use the same data to fit elastic net regularization technique. So I will scroll up and I will load the data that we have already, and all the tokenization and the features. Not feature selection, but the tokenization, and the way we use Quantida, and we also implemented TF-IDF method of feature scaling. Now I simply, because I already have created all the objectives, I simply load this object, load this data. I already saved it. So last time I have already saved it. So whenever I have finished, I save. And then with this command, every object that I created will be saved. So whenever I want to close this, I don't have to rerun everything. So I simply go up and reload this object. So every object that I have created already in this notebook will be loaded and will be ready for use. So I'll just reload this and then scroll down to my elastic net chapter. So I have already written some of the code. So what we do is we need to define the time, because we want to measure how long this modeling, the elastic net regression, takes. And then we will set seed. Of course, we want to, there is some sampling. We are using tenfold cross validation, and that will require some sort of sampling. And for that, we need to make it reproducible. And then we don't need this one actually, so I don't need that. And then elastic net, I'm just giving it a name, so I will give it elastic net 10 because I am using 10 different records. Because we have seen, if you remember from our actually last tutorial, we have said elastic net because in which your tuning parameters are lambda and alpha. Alpha will be set to 0, and with CVG eliminate function, you can get 100 different lambda values. And the same is true for lasso. You use CVG eliminate function, and it gives you 100 different lambda values, but the alpha value is set to 1. If you set alpha value of 1, that means you are running lasso regression. But if you set alpha to 0, that means you are running ridge regression. But if you cannot set alpha to 1 or 0, if you want to run elastic net, what you're going to do is you want to set alpha a set of a number of values between 0 and 1. So you start from 0 and then you go until 1. So you give, it depends, 100 or 10 or 50 different values, and you tune it. And that's what you need to do. So that means for elastic net, we have two main tuning parameters, and that's alpha, lambda, and actually the tenfold cross validation. That's what we need to do. So to fit elastic net regression, what we need is a train function. So we use train. Actually, you can also see it from the glmnet package. You can read it, the details. But the function that I would like to use is train, and then I define the x and the y variable. And then after that, I give the train df math. Maybe we can have a look at this object that we have already created. This is the train df math. Is actually you get after. So this is the kind of data that we have. So it's a very sparse. So each of the papers, the publications, they have gone through all this text analysis process, and all the words are broken down into variables. So that means we have a number of columns, actually 11,136 variables, which is highly sparse. There are so many variables that are not relevant. So that's why elastic net regression will help us remove some of those really noisy variables, which are not really relevant. And the same is true of TF-IDF version of the data. It's just simply is a scaled version of the data because we are using TF-IDF weighting, and these values will be different. Here, they are simple frequency. It's simply telling us how many times this term appeared actually in this publication in Ataguba 2020. So it appeared 2 times. But this is coronavirus, and if you look at disease, it appeared 2 times. But if we are using the TF-IDF version, that means they are weighted. So that means they are weighted by the number of times this document, this paper appears in a document at the same time across all the documents that we have. Now. So we define the x and the y variable with our train function, and we give it the method. Actually, this is from Caret, from the Caret package. So if you know Caret, so usually you give train and then you define the method, and then after that, because we are saying glmnet, we have to define the family, and we don't actually need this one also, but that means. So method is glmnet and family is binomial, as I said, because we are dealing with classification. We are using binomial, but if we are using regression, we use something else, or Gaussian, or we use Gaussian. And here, the train control, we are just giving it a train control because we want to tune, and we use this train control function from the Caret. And we give it the method is cross validation. Of course, we can also say repeated cross validation, and then number 10 repeat 3 times or something. But that will take us a long time to train, long training time. And after that, we give parallel, and the tune length is we give it 10. And with this tune length, we are telling it we want 10 different alpha values. So if you say 100, that means you want to try 100 different alpha values between actually 0 and 1. Between 0 and 100 different alpha values. But that will take us a lot of time. What we want to try is only 10 different alpha values between 0 and 1 actually. So one maybe 0.0 something, and then it goes until 0.99 or 0.1, actually 1, the lasso. So that's what the tune length does, but you can increase this number to whatever amount you want, depending on the computing resource you have, and you can run tenfold cross-validated elastic net regression. As you see, we have 3 different tuning parameters. One is the cross-validation, as usual, because we want to run tenfold cross-validation, and then we have the alpha. This is the alpha. That's alpha parameter, and we are also seeing the other one, which is the cross-validation and the lambda value. Actually, with train control, this also gives the lambda value. Yeah, so we have 2 tuning parameters, as I said. We are just using Caret to automate the process. But if you want, you can also use a different method, like you can use cbglmnet function. But for that, you need to use a for loop, and the for loop should be written like this if you want. But we're not going to use this one. What you need is you give the sequence of alpha values, that is from 0.01 to 0.99, and then you give it the value of every 0.01 step. It's going until 0.09, which will be long process, and then after that you give it the best model and you assign it as a null. Actually, you give this one deviance, not mean square error. Instead, we will use deviance. But I'm not going to run this. And then after that, what you do is this tuning process with cbglmnet. What you need is the for loop. So for I in length alpha, and then you give this cbglmnet x and y variable we define, and this one you give it binomial. And then alpha will be the iteration for each alpha, the one you mentioned here. And then you save your alpha and your deviance value here using these functions. But we're not going through this. This is a more complicated approach. Instead, we will use the easiest way of doing it, and we are going to use the Caret option. The Caret package. That would be an easier method of tuning alpha and lambda values. After that, now we're not going to run it until now, but the last one is we need to define again for TF-IDF version of the data. So we just replace that elastic net 10 with TF-IDF, and then we give the TF-IDF version of our data, and then we will run it. That's the same. We just simply run exchange the X variable, that's the TF-IDF version of the data, and then the rest of the equation will be the same. So now I will run it and pause the video. This is great. Our modeling is till the training is completed. It actually takes only 1 minute and 30 seconds for each, a little bit more than 30 seconds, but it was not really long process. But if you take this number very long, and especially if you do repeated cross validation, like repeated 5 times, 3 times, or the number you want, then this more training process will take a little bit of while, a little bit more time. Now what I want to do is we want to see how actually the details of these models. Let's see. So for example, if I simply prove the model, we'll see these values. So we have 689 different samples because we are using tenfold cross validation. We have many different samples, and then we have 11,000, more than 11,000 parameters, variables, and we are seeing summary of the sample size for our cross validation, and then we have it's doing some bootstrap sampling, and it's giving you the alpha value. It's actually it started from 0.1 and it should be going until 0.9, so it's until 1 actually. So it started from 0.1 until 1, and it's giving another 100 different lambda values. So it's giving from 0.09, and it goes until, I don't know, until the hundreds value, which is 0.39. This is just done by automatic. Caret is doing the process, and it's giving you the accuracy and the kappa value, and yeah, that's all what you have from your modeling. But if you want, you can also see the summary of your model and see the details. So these are the summary if you want. So we have the alpha, beta, and all the parameters that we have, all the variables, and then the links, the mode, and the like. We are not going through this, but what we are interested is in the names of the details, and we see the names, so we can see the method, the model info, model type, results, and we are not going to see all the other ones, so we are going to see only the best tune. So let me see what is the best tune, because we want to see which value of alpha and lambda combination is our best model. This is where our best model is. So you see our best model is on the 85th combination. We have 100 different combinations, but within the 100 combinations, we are seeing at alpha value of 0.9 and at the lambda value of 0.048 something. Our model actually worked very well. So that means the closer you get to lasso regression, that means our prediction will be, the closer the alpha gets to lasso, that means the better our model is. Actually, if you remember from our prediction, this should also signal you something, because we have seen lasso and ridge regression, and lasso is alpha value of 1, and ridge is alpha value of 0. So if you remember from our lasso regression, actually with alpha value of 1, we have seen our model actually worked very well. So 94%, 95% sensitivity, and about 90% specificity, at least in the simple frequency count. And then if we look at the TF-IDF version of our model, it was about 97%. It's even more improved, and then it goes 90%. But if you remember from the from ridge regression, that result was a little bit smaller, lower than what we have seen in the last regression. So you see here sensitivity of 98% actually, and the specificity of 91%. No, that's sigmoid. I didn't expect this would be. That's actually the best model that we had. But again, ridge regression, we have 84, 89 for the TF-IDF version of our data, and then for the simple frequency, we have seen 84, 88, and the accuracy is about 86. So that means ElasticNet is also confirming that the model ElasticNet closer to alpha value, close to lasso regression, is actually where our best model is. So let me scroll down and then continue the rest of our tutorial. So as you see, that means this is where our best model is, the alpha value of 0.9 and lambda value of 0.04. So that means we are close to the lasso model, because this is where our best model is, and we will plot. Actually, we will plot our model and see how our model looks like. We'll visualize it. To visualize, what you can do is you can simply use the plot and pass the plot function to the model, and we can also give it the title, like we give it the main equals ElasticNet. Actually, this is the TF-IDF version of the data, and for the other one, we also need to plot. And yeah. So this is how our model looks like. So you see we have different regularization parameters. So we have to edit the graph because it's going out of the margin. And to do that, we need to use a different package, this REPRR actually. Actually, you can, I already put it here. You can have a look. This is REPR for Jupyter plot options. If you use Jupyter Notebook, if you use RStudio, you may not have this problem. Otherwise, you need to redefine our plotting options. For that, what we need is we need to define our plotting options because we want to see all these regularization parameter values. So we have to redefine our plot options. For that, what you need is the options function from by default is already in our notebook. So we don't need to load the library. After that, what we need is we need this REPR plot and REPR plots, and then width actually it should be width equals. Let me make it 12, and then I'll define again for the height of my graph. Then I can actually HT no equals. Let me make it 10. Then I can actually, if it is okay, it should be okay. And now this graph, the width of this graph should be further bigger, and then all these hidden regularization parameters will be visible in my plot. So let me run this, and now we have all our actually all of our regularization values, the alpha values. So this is from 0.09, and then it goes until somewhere 0.39 something. These are all our regularization parameters, and it's mixing it with with a lambda value, and the mixing is actually calculated by the mixing percentage, and it's giving you this kind of graph. The graph is on the y-axis is accuracy, it's bootstrap accuracy, and then on the x-axis is the mixing percentage, which is a mixing of regularization parameter with lambda. This is our where our plot looks like. But if you see if you want to see where our best model is, I mean, this may be a little bit difficult, but we can scroll where our accuracy, where the bootstrap accuracy is the maximum, and we can see it should be somewhere here. This yellow value, the 0.449 regularization value, the parameter value should be this one. This value should be our best model. Actually, that was actually what we have seen. 0.09 is 0.48. That's where our best model is. So this will be the model that we're going to use for prediction. The same, we can do the same for again for the other one. Actually, it's not may not be different, but let me check again. For that, we use again for ElasticNet another TF-IDF version, and that will be again similar. So 0.9 again, that will be again where our best model is. But let me put it again, plot it, and see where that model is. So let me move this, and then see there, see the plot. So this is again this is where our best model is, around between 0.8 and 0.9 mixing percentage, and regularization parameter will be around 0.048. That will be where our best model is, and we're going to use that model for prediction. Next is prediction. We want to use these models for prediction. So for prediction, again, what we need is a predict function, of course. Then let me use predict. Elastic. For that, we need to use a predict function, and then after that, we use I call my elastic net. I think it was elastic net 10. That's my my model. So after that, I need to give it new x, actually my x data, which I can new data, and that will be df matched. If I didn't forget the name of that data, maybe df matched. No. Let me scroll up, and I forgot the name of that data. So let me scroll up, and I use. So that's the test data is a match data, which will be matched df match. So let me go back to that prediction, and let me use this matched. So that will be matched. This will be our data, and as usual, we define our best tune, the S value. Actually, we were using S value in our the S value will be where your lambda is a minimum. So that will be elastic net. We use, actually, let me put this down here. S will be elastic net 10, and we will have lambda. Actually, best tune. Hold on. It should be with SGB. Let me try it without. So let me just ignore this. Let me see what kind of error it will spit. And that will be the type will be class. and then let's see. I'm sure there will be an error. So now it's giving me type should be row or probability, so I should use row, or I can also use probability. Okay, it seems it's working. So let me see how the Fred elastic actually the prediction look like, and it's already predicted. So that means I don't need to define my table. Let me see the table. So that means I don't need to define the S. So that by default it's taking, if you do the elastic net, you don't have to define S. So that means this is a good sign. I thought we need to define S with lambda mean, but that means by default it doesn't need to make. Maybe what if we use? Let me try again, and this again with the best tune actually, best tune, and see if this will result the same. Actually, it's working the same. So it's working again. It's predicting. Yeah, it's very quick. So it was actually running, but that means if you don't also define it, it doesn't complain because it's using the best tune. Best tune is a lambda, the minimum lambda value. Actually, not the minimum lambda, the lambda value, and the value that creates the minimum, the maximum accuracy, which will be an alpha value of 0.9 and a lambda value of 0.048. That would be our best tune. So you can kind of define it, but otherwise you can also ignore it. So that will be. But if you do it this way, like if you do it, give it like probability. Let's say. Actually, it should be probability. So if you do it this way, row or probe. So it should be probe. So that means if you do probe, you need to give it a different way. You need to, because this elastic now is probability. So it's done this way. So it's giving you all these values, and it's giving you for two classes different probability. So this article, for example, for COVID, it has a probability of 0.98, but for the SARS, it has a probability of 0.016. So that means you would just need to use this one, and then you define is the probability of this part is greater than 0.5, and you define it as COVID. But if that one is greater less than 0.5, that means you define it as SARS. But that will be your cut point. But we don't need to use prop. We simply use a row, and then after that we simply classify our so that will be. So now the next thing is we need to calculate. We need to do confusion matrix. For that I'm using the conf again, conf elastic, and that will be confusion matrix. Let me pass my confusion matrix function, and then I can simply pass again the table function, because I want to tabulate the test data with the prediction. So the prediction is elastic net, and then I will again pass the test data. Test would not really, test actually. Test include. This will be giving us the confusion matrix. So if I run this now, I should be able to have my confusion matrix. So now I already have it. Actually, this model seems to be very again another container. So it seems it's working really well actually in terms of identifying the COVID papers, but in terms of identifying the SARS papers, it seems it has made some errors. Otherwise, you see the sensitivity is very strong, accuracy about 95%, again specificity of 90%, which seems to be again fantastic. So we do the same for the TF-IDF version of the data. I will simply copy this and change a few things. TF-IDF. Then I will simply pass this. I call this TF-IDF. Then again, that's our model. My model is the TF-IDF version of the data. Again, I will use the TF-IDF version of my model. Again, I will need to change this TF-IDF. The rest will be the same. Actually, we have changed everything, and then here I will simply change this. Prod here again should be TF-IDF. Now prod elastic TF-IDF predict function elastic net my model. This is my elastic net regression model, and then after that new data, the TF-IDF version of my data, and then I give the elastic net TF-IDF, which is the best tune. The best tune will be 0.9, and the mixing percentage of the lambda in the alpha values. And again, the type I just want to have label classifiers instead of probability, so I am using row. After that, I use the confusion matrix function and pass tabulated value of the prediction in the test. Now after that, I simply run both. Both are already here, and then I can simply print them out and see which part of our model actually performs better. Now let's see in the first part of our model, which we have already seen. It's 98% and 95% accuracy, and about 99% actually sensitivity, especially of 90%, which seems to be again almost identical with my with the other model. But let me see if I have already made an error in my modeling. Maybe I use a wrong data or something, because they are exactly identical, and I want to check. But as you see, I use a train mat TF-IDF, and then so that means changing the model to TF-IDF or using the simple frequency didn't change yeah, didn't change my predictions. Again, I'm using TF-IDF to predict, just to make sure that I'm using the right data and the right data for model training and prediction. But that means the two models, ElasticNet with simple frequency, ElasticNet trained by using simple frequency of our my data, or the TF-IDF version of my data. So it didn't change much of our prediction. Actually, it's identical. So the kappa is, for example, 8975, and again here. So they are identical. So now we have already completed my regularization. I will just save my model, and yeah, so now with this I save every object that I have created. So next time again I will load my object and continue to the next station, maybe which will be about XGBoost maybe. I'm not exactly sure that I will actually continue on this station. Instead I will proceed to maybe meta-analysis or something. It will be more fun to me. Yeah, maybe I will come with another text classification algorithm. Otherwise, this is what we have so far. So far we have seen ElasticNet and all these regularization models, and we have actually seen nothing beaten this convmat. What was it? Sigmoid. We have already all our objects. This was our best model, I believe. 98%, 91%. So that means this is 98%, but I think Lasso also was good. Okay. Actually, ElasticNet seems to have beaten it, but in terms of specificity, we have lost something. So still, our best model is this Sigmoid SVM with Sigmoid kernel. Yeah, I hope you have enjoyed this tutorial, and I hope I will see you again in another video. Thank you very much, and keep subscribing and following this channel. Thank you.